What is gravity?
We have no idea. Okay, next question.
I don't know.
Nobody in the entire world knows why that falls.
So what is pushing this?
Here. Why does that fall?
Newton didn't know.
We can describe it pretty accurately, but no one knows why.
We can describe gravity. We can say what it does to other things. We can measure it, predict with it.
I don't need a computer to get a kid interested in that. To spend a week playing with gravity and trying to understand it and come up with reasons why.
So what is pushing this?
I don't know.
Nobody knows why.
So Newton simply threw his hands up and said, I don't know. So I'm going to invent something called gravitational.
We have the theory of gravity. Gravity keeps you on this floor. Gravity attracts everything around its vicinity to create gravity around the Earth. Or, as we say in our astronomy courses, when we teach our kids, gravity sucks. Gravity sucks evenly. It pulls everything to the center. But then Einstein gave us a different picture. Gravity doesn't suck at all. We tell our students, we lied to you. Gravity does not pull you to the floor. Space pushes you down. Why are you sitting in your chair today? Does gravity pull you to the floor? No. There is no such thing as gravitational pull. We lied to you. The space around you is warped, and space itself is pushing you down into your chair, and that's why you're sitting in your chair today.
Why are you sitting in your chair today? Does gravity pull you to the floor? No. There is no such thing as gravitational pull. We lied to you. There is no such thing as gravitational pull. We lied to you.
That it was brushed under the carpet, a problem so great that it was brushed under the carpet for many a decade. And this is the fact that galaxies spin too fast. We believe in the work of Isaac Newton, at least on planetary scales, but when you apply Newton's laws of motion to the galaxy spins too fast. In fact, 10 times too fast. By rights, the galaxy should fly apart. Therefore, scientists said that we have to have dark matter, a halo of matter that surrounds the galaxy and holds the galaxy together.
Between 1% and 3% of the universe is all the stuff we can see, and somewhere between 99 and 97% of the universe is stuff we can't see. This dark matter that dominates our galaxy, we're virtually certain now, is made of some new type of elementary particle, different than the stuff that makes you and I up.
And what have they discovered? Absolutely nothing. Zilch. What is a little bit perturbing is that after 50 years we still haven't found what the dark matter is. But on the other hand, that doesn't mean they're not there, it just means they're harder to find than we thought.
We look out in the universe and 85% of all the gravity that's out there has some mysterious unknown source. We add up all the stars, the galaxies, the planets, the comets, the black holes, the dark clouds, everything out there that we can see, touch, smell, or taste. And it doesn't add up to give us the gravity that we see operating in this universe. So really, we should be calling it the dark force, because we don't know if it's made of matter. It could be a profound misnomer, sending people off in thought directions that might not really be the right path. So dark matter is just simply what we call this thing about which we know nothing, responsible for 85% of the gravity of the cosmos. We've known about dark matter since the 1930s. Back then it was called missing mass. That's what it was called. Because, there's got to be some mass. Where is it? We can't find it. It's got to be here somewhere, because we got the gravity. If you have the gravity, you got to have the mass. Mass and gravity go together. It's really dark gravity. Actually, we shouldn't call it anything. We should call it Fred, something that has no meaning because we don't know what it is to call it. But it is the longest standing unsolved problem in modern astrophysics. Dark matter, dark energy. Everything we know about the universe, what we're made of, galaxies, stars, planets, that's all right here. So, according to this chart, we are 96% stupid.
So the problem with cosmology is that we keep inventing theories, ad hoc theories, to try to explain the data, such as inflation, dark matter, dark energy, and so on, just to keep patching the theory up.
There is a crisis in cosmology. Usually in science, if we're off by a factor of 2 or a factor of 10, we call that horrible. We say something's wrong with the theory. We're off by a factor of 10. However, in cosmology, we're off by a factor of 10 to the 120. That is 1 with 120 zeros after it. This is the largest mismatch between theory and experiment in the history of science.
We know exactly what gravity is, right? We can go deeper into Einstein's understanding of it appearing to be, space-time warping, but again, we still don't know what the underlying cause of all that going on is. We don't know. Well, we call that attractive force gravity. Well, we call that attractive force gravity. Don't know what gravity is yet. We're still working on that.
Now, back to the point. So if you can't observe gravity and you don't know what gravity is, how are you able to make the claim that it is gravity doing what you're claiming? Again, you've never observed gravity. You claim it's not a force. We've observed the effects of it. You've claimed it's not a force, yet you require yet you require a force.
Yeah, the force created by gravity, the force of gravity. Yeah, no problem. Well, we call that attractive force gravity. Don't know what gravity is yet. We're still working on that.
You are claiming when we see an acceleration like a skydiver falling to the ground, it's mass. You would say the cause is the mass causing attracted to mass, inversely proportional to its distance or whatever. Great. Now you figured out the cause for that acceleration, which requires a force. You then made a claim that the force which is causing this acceleration is gravity. You can't now say the acceleration between the masses is gravity if you're saying the force is caused by gravity, which causes this. So gravity can't cause gravity if you don't even know what gravity is and you've never been able to observe it. Now, the problem you also fall with is, based on today's science, quote-unquote science, which isn't science, it's not a force, so you can't claim it to be a force anyway, and it's not observable because it's in the fourth dimension. So you sit with you catch with the catch-22 problem here. You don't know what gravity is. You claim it to be a force which causes the acceleration, and not a force at the same time. That's not observable because it's in the fourth dimension.
I didn't ever claim that gravity is a force. Please stop putting those words in my mouth.
Atmosphere.
Atmosphere?
Yeah.
So do you believe that sphere-shaped air is something we experience?
Why don't you explain to me what you perceive it to be?
It's your word. You said atmosphere. What do you think that means?
That is the amount of gases that are held within the Earth by gravity.
Held? Gravity doesn't hold anything. It's not a force. There's no scientific evidence of gravity.
Really?
Middle of a statement.
Middle
of a statement. My bad. Obviously, it's me being a dick wanting to make a false statement, contradicting you. Obviously, that's me being a dick. No, there is no force
that's
of
fine.
gravity.
No, go right. We can-
My
we
bad,
can-
still
we
in the
can
middle of the
go
same
right.
sentence. Obviously,
I
this
love
is me being a
This is
dick.
fine.
Maybe this is me interrupting you. So gravity's not a force.
Which you've been doing the whole show.
My bad,
but
that's the
okay.
fourth attempt. Gravity's not a force to hold gas in a sphere shape. Gravity is the bending of a conceptual medium known as pseudo-Riemannian force space-time derived in the mind's eye of Einstein in mathematics. It's a fourth-dimensional geometry. Meanwhile, in reality, we live in a three-dimensional Euclidean reality. There is no dimension of time to bend. Even if we could bend time as a dimension in a Euclidean four-space geometry, it wouldn't be a container for gas. Gas isn't held by pseudo-Riemannian force-space time bending in an Einsteinian gravitational dimension. Further to that, the notion that gas being held, i.e. gravity is a force, was debunked by Einstein 108 years ago. Mass does not attract mass. That's a Newtonian concept of gas. Pressure being held because of its weight going down towards the centre of Earth. That was superseded 108 years ago by Einstein when he developed the fourth-dimensional space-time bending, which is not a force and is definitely not a container to hold gas in a sphere shape. So your oxymoron, sphere-shaped air, is merely a begging the question fallacy to allow you to describe atmospheric conditions as based on an R value, a sphere value, the radius of Earth being the value that derives your refraction rate at 7/6 of the radius in sphere-shaped air. Atmo, air, sphere, a shape. Air doesn't take the shape of a sphere, it takes the shape of its containment. If the gas was in a sky vacuum, we'd have none to breathe. We'd all be dead, because gas fills space. Gravity's not a force. Bending fourth-dimensional space-time doesn't hold it in a container.
If I could...
Yes. Just one sec. Brenda's being asked.
Nathan?
You're talking straight. Very rude. Brenda's not going to get happy quick. She'll start rumpusing everyone.
No, I try very hard not to do that.
Jolly good. But it is you I'm talking to, so I'm in your...
Yeah, space-time is the invariant property, right? Simply distance, the distance is without considering time, that isn't invariant.
I'm not asking what it isn't. Yeah, distance is easily describable in one of the three dimensions that we do actually experience. You've said that that's time. It isn't. Distance isn't time.
In order to locate an object, you need to provide where it is and when it is.
Do I?
Yeah, so that's
no,
four
you don't,
coordinates.
because you only exist in the present. This is silly. Why do you keep talking?
Of course you exist in the past. Of course you do.
Okay, can you show me that? That's the third time I've asked.
Oh yeah, there are events in which, or observers in which, the past for one observer.
Brenda, he asked you to show him, which means you should have an example ready.
He was detailing one.
Yeah, when particles move at relativistic speeds, the future of one particle can be in the past of another.
Sorry, where does that get shown as an example?
These are fairly standard scientific results that show that the past for one observer will experience, the future.
Brenda, you're blowing it.
Okay,
You're blowing it hard.
I really don't need any help. Thank you, though. Okay, I'm trying to get you to show me something that shows a fourth dimensional time.
Yeah, it is the coordinates necessary, right, to uniquely identify something, because it simply is an experimental observable fact, right, that for some particles, their future is in another particle's past.
I heard your claim. I'm asking where I am shown that.
Through experimental observation.
Okay, so what was the experiment called? What was the independent variable? And what was the observed phenomena then?
Well, for instance, when cosmic rays strike the upper atmosphere, they generate muons. The muons experience time because they're traveling very fast. They experience time slower than we do.
It's another way of saying she can't show this. This is just ridiculous. It's all presupposition.
I just told you.
It's ridiculous.
I just told you that
She's not going to show you. She can't.
I just told you. The particle decay, the decay time for
coordinates.
muons is slow.
You're describing coordinates of something, and you said it was experimentally valid. So what's the natural phenomena? Is it the observation of muons?
It's the time it takes for a muon to decay.
Shout out to Jason Reed. I agree. Please have Brendan not stop talking. Thanks for the super chat. No. So far you've given us coordinates, but it doesn't demonstrate a fourth dimensional time. And the reason is because it's only in existence in Einstein's mathematics. That's where it exists. It doesn't exist in physical reality. And you know that because he labelled it such. Pseudo-Riemannian four-space-time geometry is pseudo. It's definitely not scientifically validated. Even Einstein, the man who invented it, labelled it pseudo as a geometry. That's descriptions in maths. That's not anything in physical reality, Brenda.
Oh, so pseudo there doesn't mean what you seem to think it means. It simply refers to it's not a.
I think I've been offered muons. Are they the observed phenomena in the experiment? It's not segue. That's what I was on.
The time it takes for them to decay is longer when they're created by cosmic rays because they travel at relativistic speeds.
Right, the time they take to decay, how long they decay isn't a dimension, is it?
Time is, yes.
It's like you described how long something decays in a given period. That's not a dimension. That's how long something decays by way of a description arbitrarily ascribed by us when we deliver the concept that we note as time. When things pass through our known existence, that's how we describe them. But it isn't a dimension.
You're just repeating the claim.
Well, you're yet to show me a pseudo fourth dimension of time.
I did. I gave you the observation that muons take longer to decay.
I got that.
When they're created in the upper atmosphere because they're traveling at relativistic speeds.
You said it was science, and I said, what's the dependent variable observed phenomena then? Is it muons? No answer. Is it muons? Second time I'm asking.
Observations are part of science.
Is it muons that is the quote from you scientific part of it? That would be dependent variable. Is that what the dependent variable is or not?
Right. So observations are part of science.
Yeah, I got it. Observation, muon. So therefore, muon, yes. Dependent variable, Nathan, yes. Or no, not the dependent variable. Which is it? It's the fourth time I've asked.
Yeah, when muons are not traveling at relativistic speeds, they decay much quicker.
Yeah, I heard that 4 times. Is that the dependent variable in this science? Yes or no?
It's not an experimental setup. It's an
so when you said it was
observation.
science, you were just doing what we discussed in the pre-show where we say people who don't have science lie, call things that are pseudoscience and made up garbage and pseudo fourth dimensions. They call them science like you just did. So it's not experimental, therefore not science like you boldly lied about. What an outrage. So when it comes down to the nitty-gritty of what you've actually bullshitted about and said is science, it isn't, making you a liar. So why are you lying to us about it being science when I've already taken it to pieces as pseudo-geometry from Einstein? It's not science. You're a liar. I don't want to talk to this person anymore. I don't want to talk to you anymore. You're a liar. You said it was science and it isn't. I don't like being lied to. I don't like me having to ask you 4 times what the independent variable is while you weasel and worm your way around the fact you haven't got one and then tell me it's not experimental, therefore not science, making you an outright bloody liar.
And that's false. Observations are part of science.
We established what science was before this discussion.
As for why objects fall downwards when dropped, rather than upwards or sideways, firstly, There is a pressure gradient formed by the amount of stacked air, water, and land over you in a column, which increases the pressure, weight, and density the farther down you go, and that defines direction. Secondly, helium balloons fall up, not down, proving there is no downward directional bias. You can also prove this point by throwing various kinds of rocks, including pumice, into a pond. All rocks, excluding the pumice stone, will sink to the bottom. But then when you throw in the pumice, it will rise right back to the surface. This is because pumice has a density less than water, just like helium balloons have a density less than air. Their relative density, being lower than the medium surrounding, causes them to rise, just as things with a relative density higher than the medium surrounding causes them to fall. This is as for why objects fall downwards when dropped. The British scientist, Freemason, and wealthy grandson of the Duke of Devonshire created an experiment which he claimed successfully proved the existence of gravity, measured its constant, and provided accurate figures for the exact masses of the Earth, Sun, Moon, and planets. How did Cavendish achieve this quantum leap for heliocentric pseudoscience? He fixed 2 large lead balls on opposite ends of a torsion balance and hung them from the roof of his shed. By watching and recording slight motions of the contraption via telescope through his shed window so his mass would not affect the reading, Cavendish claimed to have proven gravity. 2 small lead balls were hung near the large ones, and any motion observed towards one another was touted as being the influence of gravity. Now, the Cavendish experiment has been widely criticized by the scientific community because never in over 2 centuries since its creation has anyone been able to replicate it. Firstly, the balls simply do not always attract one another, as they must, for the so-called gravitational constant to be constant at all. Sometimes the torsion balance turns towards the balls, and sometimes away, as it is impossible not to give some slight tremulous motion when interacting with it. Henry even complained in his notes how often as he was performing the measurement, the contraption was still in oscillation. Secondly, since his calculated force of gravity was 10 to the 39th power weaker than the force of electromagnetism, from which all material objects are composed, there is no control for the experiment, which can factor out and positively differentiate the alleged gravitational force from the known, stronger electromagnetic force. In other words, the balls could simply be attracting each other through static electricity, a known force existing in all things, billions of times stronger than gravity, and impossible to control for the experiment. Even though no one could replicate Cavendish's findings, the experiment went down in history as a great success, and is still taught as veritable proof of universal gravitation in science textbooks today. Then it is not in violation of any action against infinite properties to say that an infinite universe means there's an infinite amount of matter, and to arrange this infinite matter to form what we observe to be our reality, which is that there is a density gradient in which we exist, where all matter below us is more dense, and all matter above us is less dense. Now, rather than assume the existence of having a gaseous atmosphere hovering around a ball in a vacuum, which violates many laws of physics, instead, imagine we live on an infinite plane with a density gradient. Solid matter forms the land below us. Less dense matter forms the fluids on top of that, and even less dense matter forms the gaseous atmosphere we have above the solid surface. Now, it's not to say that space is a vacuum, but rather, as we climb further up the density gradient, eventually we reach a point where any particle is more dense than the lack thereof any particles, or the void. Since the void is less dense than any gaseous particle, or any particle at all, it supersedes any particle, and thus arranges itself above the particle atmosphere. Space, in this instance, would not be a vacuum, but rather a gradual taper in density up to the point of there only being a void. And this void,
since the universe is assumed infinite, goes on forever, simply for the fact that any particle would be sunk down below it. Also, I made the mistake of saying that gaseous particles are the least dense form of matter, when in fact highly charged plasmas are actually the least dense form of matter. And seeing that these plasmas have an excited and high energy level, that, along with the fact that heat rises, as well as less dense matter rises, you then have scattered bodies of radiant plasmas in the skies, much further than the gaseous atmospheric band of gas molecules. And these plasmic luminaries exist in an environment of such little friction that they themselves move about at such immense velocities whereas to create the stellar motions. Now one should take into account that plasmic matter also forms magnetic qualities, either positively or negatively charged, or both at dipoles, so much so as to cause these objects to spin individually and also rotate collectively around the central northern magnetic pole in the center of the flat Earth plane. So none of this proposed violates any known laws of physics and offers no contradictions as to its mechanics and function, which is more than can be said about the ludicrous ball Earth model, which is cram-packed with violations, fallacies, and incoherence of known physical laws. To think that the reason you are pressed to the ground is because the ground is constantly pulling you down is as flawed as saying a helium balloon rises because the ceiling is pulling it up. Clearly, in this example, it is not the ceiling of the auditorium pulling the balloon to it, because if you remove the ceiling, the balloon still rises, having nothing to do with the ceiling. So if this is true, and is proven to be so, then one can conclude that the reason we are pressed to the ground has nothing to do with the ground, but rather that the ground is just a barrier in the way of our trajectory down the density gradient. As anyone can test for themselves, as you remove the ground from under you, you continue to fall downward until you're met with more solid barrier matter. So if we were to remove the ground completely, we would descend down the density gradient until we reach the point of density equilibrium in which we would float freely amongst other similarly dense matter. And once this point is reached, particles can float about freely in whatever direction they want. Hence why air molecules, being in their density equilibrium point, neither fall nor rise, but rather flow about freely moving whichever way the wind blows them. Now as humans have a density equilibrium point a little above water, and hence why we fall through the gaseous atmosphere but float up in water, and coincidentally while in water, we can move about in all three-dimensional directions, something we can't do in air, and this lines up perfectly with the scientific notion that we are upwards of 70% water, which would mean that the remaining 30% of us that isn't water is comprised of matter less dense than water, and hence why we float in it. And although some of that matter, like bone matter, is more dense, other parts, like the air in our lungs, and therefore all throughout our bloodstream, average out the remaining 30% of non-water matter. Now, one must realize that it takes no energy to remain afloat on water, like when doing a back float, but it takes much energy for birds, for instance, to stay airborne in the air, because they are not at their density equilibrium point when flying. In conclusion, let's consider the following proven facts of physics versus the supposed effects of gravity. It is a fact that objects set in motion in a straight line in a frictionless environment continue to move in a straight line, while objects at rest remain at rest. Unless gravity exists, then whatever object launched the original object into motion would cause the object moving in a straight line to eventually slow down, stop, and start heading back towards the launching mechanism. It is a fact that a spinning tethered object, once the tether is broken, immediately starts traveling in a straight line tangent to the circle it was rotating around. Unless gravity exists, then objects will just continue to orbit with or without the tether, as they claim the sun and planets do. It is a fact that any non-adhered substance or object on the outer surface of a spinning object will fly off from the equatorial line of rotation. Unless gravity exists, then everything just perfectly sticks to spinning objects without there being the slightest outward push from the spin or inward pull from gravity. It is supposedly a fact of gravity that objects of different masses all fall at the same rate. Unless you have a helium balloon handy, in which case it won't fall at all and will rise upwards instead. It is supposedly a fact of gravity that two objects of appropriate mass will orbit each other based solely on their relative mass to one another. Unless you require an actual demonstration, an empirical scientific experiment showing it, in which case it has never been done. And the questions continue. How or why would huge solid planets orbit around a giant flaming ball of gas? What is orbit, and why is it never observed, but is the reason why the Earth goes around the Sun? And the Moon around the Earth, but nothing on any smaller scale ever orbits. Why would water stick to the outside of a convex surface? How do we stick to the outside of a ball that's spinning and orbiting 30 to friction? How does the Earth propel itself to remain in constant motion around the Sun without any fuel or burning any energy to sustain such immense velocities? How does the Moon go around the Earth with no energy required at such a grueling pace? How does any of this take place without any form of energy consumption to maintain these outlandish motions and velocities? All of these questions present problems that the theory of gravity simply cannot explain. Can you see how many facts of physics gravity just brushes by the wayside? But we do believe that we have an explanation. You know how beyond 10 miles out to sea, the laws of the land no longer apply, because you are no longer in any national jurisdiction? Well, that is 10 miles horizontally. What most people don't know is that if you travel 10 miles vertically, you are no longer subject to the laws of physics, because you're no longer in any academic jurisdiction.
Right, was in your recent exchange with MC Toon that got a little bit heated, where you were continually asking this question of what is gravity. So I thought that we could maybe start on that point. That's probably a good point to start off on a gravity debate, right?
100%, yeah, that'd be great.
Sweet. So I want to clarify here, because there's two meanings to what gravity is, depending on if you're talking about classical mechanics, aka Newtonian mechanics, or if you're talking about Einsteinian general relativity. So I think that the distinction there is where a lot of the confusion is coming into play, where you're saying, does gravity cause gravity because F equals ma? And this whole thing would be kind of a confusion within Newtonian mechanics. And then there's a difference with Einsteinian general relativity. So just if I can define it within both regimes, just so we're on the same page, I think you know this, but I'll just put it out there for everyone so we're on the same page here. In Newtonian mechanics, gravity is an attractive force between masses. In Einsteinian general relativity, gravity is the curvature of space-time that results from mass energy. So in the general relativity lens, the actual force that is the gravity in Newtonian mechanics is a pseudo-force. That doesn't mean you can't measure it. You can still measure it in newtons, just like you can measure other pseudo-forces, like centripetal force or centrifugal force. You can still measure those in experiments with units of force, newtons, but they are technically pseudo-forces, which depend on your frame of reference. So it's the same case with gravity under the general relativity regime. So I assume that most of this conversation will be talking about gravity being the curvature of space-time in general relativity.
Yeah, sorry, my daughter. Sorry, my daughter. Okay, from Mama Soppy. Sorry, my daughter's asked for.
Yeah, no worries. But that was basically was going to be my point. Was that I think we could talk about how we know that gravity is curvature of space-time, and I kind of brought three main lines of evidence to support that claim.
Okay, yeah, because you know what I'm going to ask straight away. Can you back this claim up?
Yeah. So the three things that I would point to, and I think that they're all super interesting, but just in order of what I find the most interesting, gravity waves, gravitational redshift, and gravitational lensing would be the three things I would immediately point to substantiate the claim that gravity is space-time curvature. And if you want, when you say that gravity causes gravity, right? Just so that we can clarify that, what I would consider to be a misunderstanding, but I'll give you a little bit of credit, because I think you could kind of say that Einsteinian gravity causes Newtonian gravity. because obviously Newtonian gravity, which is that pseudo force, that the acceleration and the force are both caused by the curvature of space-time. So what we would call gravity under a Newtonian regime would be caused by the curvature of space-time, which is gravity in an Einsteinian regime. So I don't think you're wrong to say that Einsteinian gravity causes Newtonian gravity. It's just not the way that you would be learning about it in a physics textbook. But I think in a technical sense, you could get away with saying something like that.
Okay, yeah, because that's the thing. That's what I was saying. So you guys are claiming gravity caused gravity, and if you're saying, okay, it's the mathematical construct in the fourth dimension causing a physical force to appear, you don't see the problem, because let's, for instance, say
For a second right there. I don't mean to cut you off, but just right there with how you summarize that, it's not necessarily in the fourth dimension, right? The fourth dimension would just be time. So it's within space-time, which is four-dimensional. It is not the fourth dimension. It's just a four-dimensional manifold.
Yeah, but we are three-dimensional beings, so we aren't able to observe in the fourth dimension.
No, we are four-dimensional because we exist within space-time, which has four dimensions.
You see,
so
that's where I disagree
we
with
are
you.
three-dimensional in terms of spatial dimensions, but in terms of all dimensions, we're four-dimensional because of time.
But time's a man-made construct. Time doesn't exist.
It really is not insofar as the symmetries of Lorentz transformations are concerned, which is why space-time is just one thing and not space and time. It's because of the symmetries during Lorentz transformations within like Minkowski space. It's very mathematical, but there is a reason why time is not simply a man-made construct. Now, when you're talking about the measurements of time, okay, sorry.
How would you go to providing evidence that time is not just mathematical?
Time is not just because we can measure the differences in time dilation due to gravity. That's what gravitational redshift is. It's a direct observation of the curvature of space-time from gravity.
No, that's what I'm asking. You're saying time is not just a concept, so I'm asking you, what would you be to base on actual showing time is physical? That's not just a concept, because time would physically have
due to gravity. That demonstrates that it's not just a construct.
But that's again just you begging the question. It's due to gravity. You're saying I see time dilation, therefore gravity. That's just circular reasoning.
I failed to. Could you extrapolate on why you think that that's circular reasoning? Where is the circularity involved?
I just explained it. Time dilation, therefore gravity. You understand? Because that's exactly what you're saying. You're saying because we see time dilation, therefore time is bending thanks to gravity. So it's circular reasoning.
So gravitational redshift, right? We have a one-dimensional lattice of molecular clocks, right? Each one is beating at the same time, pulsing at the exact same rate. When you align them all so that they're all at the equal altitude, they all go in unison at the same rate. But when you rotate it just to be vertical along gravity, you see that the rates change now as a result of their altitude. So this is demonstrating that gravity is changing the time dilation effects.
Could it be density that's changing it and not gravity?
It could not, no.
Why not?
Because the density has not changed. When you rotate it this way or this way, the relative density hasn't changed at all because it's within a vacuum chamber.
But what happens to the center of mass when you turn something vertical?
It doesn't change. It's still in the center of that one-dimensional lattice.
No, remember, if you got two timepieces together like this, there's the center of mass in the one, here's the center of mass in the other. As soon as you're turning it up, the center of mass is now the force, it's forcing itself vertically down now, not...
So, here you go. The center of mass is right here at the point where my fingers meet. If I turn my fingers right here, the center of mass is still that point where my fingers meet.
Yeah, but the vector,
it hasn't changed.
But the vector has changed.
But that doesn't change the density.
The density... The density is what gives the vector.
I'll provide you a source for this.
The density is what gives the vector. And this can be scientifically validated.
The density is what gives... No, I don't think that is the case, sir. Because it's in a vacuum, so the relative density is equal in all directions.
Yes, vacuum. Why do you think they do it in a vacuum?
Because it would be incredibly, like, we're talking about an optical lattice and trapping individual atoms within that lattice. If you don't do that in a vacuum, the air molecules will just cause those ultra cold cesium atoms to bounce out of the lattice. I'm talking about a very specific source right here.
Yeah.
Would you rather I send it to you, or
You can share your screen,
Okay.
but like I'm trying to say, the reason they do it in a vacuum is because they're manipulating the density, the medium, the ratios of the two density. They're not manipulating gravity. So you're begging the question and saying, let's manipulate the density medium ratio, is not manipulating gravity. So you can't claim it to be gravity.
So the density has not changed regardless of the orientation of the
The
vacuum
ratio has
capsule.
changed. The ratio has changed because the medium and between the object and the medium around it ratio has changed because you've removed the medium. So once you remove the medium,
I'm
the
sorry,
density
I don't mean to
ratio.
interrupt, but I don't understand what you're talking about. Density is mass over volume. You have not changed the mass or the volume, so the density is
The
unchanged.
ratio. Let's, for instance, say it's how can I put this on? Have you ever seen Sleeping Warriors egg experiment before? You've obviously done this experiment at school where they stick an egg in water, and if you change the density of the water, like to saline water, then it floats. It
Sure.
accelerates upwards. You change the density of the water. So you change the density medium ratio of between the object and the medium. So let's take that water away now. The egg cannot be supported because it's no longer less denser than the medium. So you're changing the ratios between the two, and that's what gives its vector. And that's exactly what I'm saying. When you're sticking anything in a vacuum, you're removing the medium, so you're changing the density ratio between the object and the medium. So in other words,
So
it's
a couple
not
things
gravity.
A couple things on that. One, obviously, there is no vector in that case, but
yes, there is.
I just want to clarify that whether or not the vacuum capsule is this orientation or this orientation, none of the relative densities have changed. There is no change in density, regardless of if you tilt it this way or this way.
Remember, the vector is always pushing downwards. You would
Why?
agree with that? Because the
I
medium,
would, but I would agree
the
with
medium,
it because that's gravity.
because
It's
the
going-
medium cannot support the object.
But
So-
it can't support it up or down, so why just down?
Because you've taken the medium away, the only medium that can support it to keep it up.
But
Pressure,
why
because of
doesn't it
pressure
support
mediation.
it- But why doesn't it support it to keep it down? You see, you're just
Why? Because
you're not,
because
you're
you've
just
taken because you've taken the medium away. When you have a
Yes.
denser medium, this is how the relative density ratios work.
okay.
When the medium is denser, then it goes up. But because you take the density away, it can only go down because it can't be supported by the medium.
Okay, I'm going to stop sharing my screen here because I was just trying to provide the citation for that what I was talking about specifically. But since we're talking about the downward vector here, I just want to make sure, because it sounds like you're just arbitrarily applying the downward vector. If we do a thought experiment real quick, where you have an apple in a vacuum chamber with equal density in every direction, there is no preferential direction in terms of a density gradient. It's equal. It's in a vacuum, so it's the same density above it and below it.
Mm-hmm.
Why does it go down instead of going up?
Because
when you say that
because it can't
there's no
support it.
when you say that it is not supported, why it's not supported up or down? So why does it go down if it's not supported in all directions equally?
Because there's no support. When you
But why
this
does
is
the
how
support
this is how
only
nature
need to be down?
this is how nature works. You have water on the ground, correct? You don't have water floating in midair because it's denser. That's how the
But
structure
why do things
works.
go down instead of up?
Because
Gravity
it's-
explains that. It gives a
No,
very good reason why
Gravity
that is.
doesn't. Gravity doesn't explain anything. Gravity just gives a mathematical construct based on more mathematical constructs and wants you to beg the question. Gravity cannot explain the reason why we have things going up and down scientifically, where relative density disequilibrium, you can do actual experimentation proving that there's a vector and a magnitude based on the density ratios.
Again, though, you can't prove that the vector is because of density. Because when you say that it's unsupported below it, it's also unsupported above it. It seems like you're just saying it is a brute fact of nature that the direction of that vector is downwards rather than upwards.
Okay.
Which I don't accept as an explanation. That's
Okay.
just a brute fact.
I can give you
That's
another.
not
I can give you another
an
analogy. I can give you another analogy. Law of nature, like entropy. You would agree that always high to low, hot to cold.
But we can explain that. There's a reason.
Wait. Yes, we can explain that. But can you give the reason why entropy does that?
Yes, I can.
Okay, why does entropy do that?
It's because of statistical mechanics.
False.
If you
That's
count up
mathematical.
all the number of, just let me finish my explanation first, please. If you count up all the different possible microstates of that state, the total number of microstates in which you have very, very ordered arrays versus more spread out, the sheer number statistically is going to trend towards the higher entropy because there's many more possible states for that system that have higher entropy rather than the number of states that have lower entropy. So it's a basic statistics.
Statistical is only mathematical constructing. It's just a language. Now, you said you can explain why entropy does that. You giving
I just did.
No, you gave a statistical anomaly on what it could be. I mean, I can give statistics on people betting and giving winning the lotto. That is not the cause for people winning. That's only statistics based on that. Now,
But hold on, because we're not explaining why people win the lotto. What we're explaining is why only a small number of people win the lotto, and the statistics does explain that in the same way that the statistics explains why entropy increases.
No, again, entropy is not explainable. You can statistically you can statistically give its behavior based on natural tendencies. That's why it's called the natural law. You don't know why entropy does this. You can't.
But I just explained to you why.
You gave statistics to say it's more likely to happen. That doesn't say why it does it. You understand? Likely to happen and why it happens is two different things. Now the same.
No, it explains why because of the likelihood.
No, you're not giving the cause.
The cause is it is much more statistically unlikely for entropy to decrease in an isolated system than to increase, which is much more statistically likely.
Okay,
that is the reason.
You would understand mathematics is only a descriptive language. It's not reality. It's not physical.
I agree. The map is not the territory.
So mathematics and statistics is not the cause for entropy.
The reasoning of the mathematics is still the reasoning for the observed results. It's not like I'm saying because these squiggly lines on paper, therefore the results. I'm saying these squiggly lines on paper actually represent what is going on in reality. They are descriptive of reality. If you think about all the different possible states that the system can be in, every single possibility, statistically, the possible microstates that are low entropy are such a small amount of number relative to the total possible states. That is the reason why entropy increases, because of the statistical likelihoods of the possible states. That is the reason why.
Okay, but then I can say, then why can't it just go to the most least likely statistical state then?
It can. That is possible, yes.
So
it's just very statistically unlikely.
So then statistics doesn't say why entropy, then it's just giving a statistical value based on what could happen, not what is happening.
I would say that is why, but okay, if you disagree that is somehow, for some reason, that explanation doesn't count as an explanation, I don't understand why you disagree with that, but that is the explanation.
Okay, but now let's move it back to relative density, like I'm saying. So when you remove a medium to support it, it will always go down. This is a fact. There's no statistics about it. If you remove the density of the medium, it will go down. This is observed in nature. It's always that. If the object is less dense, it will go up. If it has displacement, Archimedes principle, it goes up. Okay. This is observed in nature. We can do science, using the scientific method to represent and experiment to show changing the ratios between densities gives either a vector up or down, and it gives a magnitude. Now, when you guys take your object and stick it in a vacuum, you're not doing science based on gravity. You're doing science based on manipulating the medium, so relative density.
Let me just be very clear here. When you're talking about density and buoyancy, you're still talking about gravity, because obviously gravity is still involved there.
No, I'm talking about relative density disequilibrium.
Are you familiar with the free body diagram?
Yeah.
So yeah, it just shows you the object, and it shows every single force that's acting on that object, including pseudo forces. And when you do that, you still have the downward vector of gravity. You just have a larger force upwards from the buoyancy. And the buoyancy, the formula involves gravity in the formula for buoyancy.
Okay. Do you know Archimedes' principle preceded Newtonian 1,900 years? And they used Archimedes' principle without G in it. So how can it be gravity then?
Because Archimedes' principle is not the same thing as measuring the buoyant force.
Archimedes' principle is the buoyant force.
Not quite. I mean, Archimedes' principle is based on the displacement, which is about the weight, which has gravity to it.
No, there's no gravity. Weight is not gravity.
Well, weight is a force that's imparted based on gravity. So
pressure. Yeah. So we can agree then, my mouse has a pressure, it has a force on my hand now. It's causing pressure on my hand. Correct?
Well, force is not equal to pressure. There's a difference of units there, but it's, force divided by area.
Okay,
so
yes, PSI.
Sure, there is both a force and a pressure.
Great, but it has a pressure on my hand.
Sure, and that is imparted by gravity under the basic scientific paradigm.
There's no science for gravity. That's what I'm trying to get you to understand.
Well,
in reality,
I mean, that's not true, though.
No, I know it's true. Based in reality, can you give me one scientific hypothesis and experiment for gravity, please?
Yes, absolutely. The detection of gravity waves by light.
That's not scientific. As an experiment works.
Sure. Oh, you want me to explain? So in an experiment, like, first of all, you come up with a hypothesis. That's a basic prediction of what results you should observe. And yeah, a hypothesis.
Step one. What's step one?
Okay, you want me to go through observation, hypothesis, then you have your experiment after you make your prediction where you have an independent and a dependent variable. You measure the dependent variable, you get your results, and you publish them. There you go. Peer review.
Okay, so we observe a natural phenomena. Correct? Where do we observe a natural phenomena for gravity?
Gravitational waves.
What's a gravitational wave? Where do you observe gravitational waves?
There are two independent methods of observing gravitational waves, completely independent from each other. The first one was at 2015 at LIGO, a giant laser interferometer, and the second one was just in June of this last year using a pulsar array.
So in other words, man-made conjuring up of a apparatus. Is that what you're saying? So if I can if I can make a time warp machine, does that now make time real?
No, but I'd be very much interested in your time warp machine.
But you understand what I'm saying?
Well, hold on. I'm saying if you did make a time warp machine, then it would support whatever your theoretical framework was in the designing of that time warp machine.
But you see the problem.
If general relativity makes a prediction about what we should see, and then if you want to say it's not an experiment, it's just an observation of gravity, that's fine. I'll accept that. But it's an observation of gravitational waves. If you want an experiment, we can talk about the Cavendish experiment where there's an actual independent and dependent variable if you're more comfortable with that.
Okay. First, I'm going to say, you didn't have an observed phenomena for gravity. If you first have to have the observed natural phenomena before you can do a hypothesis to have an experiment.
Gravitational waves would be the observed natural phenomenon.
But you said LIGO, so you guys had gravitational waves before LIGO, remember?
Yes, they were predicted many decades before LIGO.
So then it was an observed natural phenomena then?
So you're saying that in order to have a hypothesis that makes a prediction, it has to be based on these observations, even though,
It's called
they
natural.
were predicted mathematically in the framework of general relativity.
Again, so when we present, that's why it comes to pseudoscience. It's just circular reasoning again. If you're going to claim gravitational waves and gravitational lensing or whatever,
Yeah.
you have to first get gravity. To make it science, you have to manipulate the independent variable. So that's what I'm asking. You claiming LIGO is now gravitational waves, that's your observed phenomenon. Fine. What is your hypothesis for this? How are you going to experiment?
So general relativity was the framework that allowed us to hypothesize a prediction that gravitational waves should be observed if we set up an experiment like LIGO. So there's the hypothesis, the prediction.
But that's not manipulating the independent variable. What's the independent variable?
Well, LIGO was an observatory. So if you want, like I said, if you really want an experiment with an independent and a dependent variable rather than just an observation of gravity, which LIGO is an observation of gravitational waves, if you want an experiment where you have an independent and a dependent variable, then I would point to the Cavendish experiment.
I don't think you want to go to Cavendish because it wasn't an experiment at all.
Well, I can explain to you what the independent and dependent variables were.
That'd be great.
Okay, so the dependent variable in the Cavendish experiment was the torsion force on the wire, which we measured using the torsion wire. That's the dependent variable. What this variable depends on is how close the two masses are. Hold on, I've got a.
So the effect is the
Let me pull up a
torsion.
little picture for the people listening here. Can you share my screen?
Yeah, so you're saying the effect is the torsion.
Yes, so the dependent variable that was measured is the torsion in the wire here. And then the independent variable is these masses here that are moved closer to the smaller masses, which then are attracted to the bigger masses and spin the whole system clockwise, which imparts torsion on the wire. So the independent variable is how close those two big masses are to the smaller masses, and the dependent variable is the torsion on the wire.
So the independent variable, is it mass or is it distance of mass?
It basically, because in Newton's formula, the gravitational force is dependent on both the mass and the distance. By moving those masses closer, you are effectively increasing the strength of gravity on the free body diagrams of those small m masses. So your independent variable is effectively gravity.
Okay, so no, there's no gravity here. You're just showing torsion twist due to the
wait, hold on. We're not talking. I said the independent variable was gravity. The dependent video.
So how do you manipulate gravity? So please manipulate gravity for me.
Yes, that is what this experiment is doing.
No, you doing mass and distances. That's not gravity. You said gravity.
That does change the force of gravity.
No, you said gravity is the independent variable, not the mass and the distance.
So imagine, okay, here we go. You said you know what a free body diagram is. So if we draw a free body diagram for this small m mass, right? You have the gravity that's going downward, and this is just, in the physics consensus. I'm not saying that, you accept that any of these are real. I'm just saying that if you were in a physics class and you were being graded, you would draw a free body diagram for the small m mass. There would be, first of all, there would be the force going down from the Earth's gravity, and there would be another vector of attractive force towards the big M. And as you move that big M from the free body diagram of the small m, the magnitude of that vector increases. Therefore, what you are doing is manipulating the strength, the magnitude of that gravity vector. That is what you are doing.
That's why I'm disagreeing with you. You're already begging the question that it is gravity and gravity is a force. You're already placing. No. This doesn't show gravity. You claiming that gravity is the cause, but you're not manipulating gravity. You're manipulating mass and the distance between the masses.
That does manipulate gravity, though.
What's gravity? How's that manipulating gravity? When it comes to scientific hypothesis, you're supposed to have the IV and the DV. If your IV is gravity, that is supposed to be what you're manipulating. You're not manipulating gravity.
So
you're not manipulating gravity.
In the Newtonian regime, where gravity is the attractive force between masses, when you move that big M mass closer, what you are doing is increasing the force of attraction between masses, which you are measuring as the dependent variable as a torsion in the wire. That is the IV and dV, and the IV is effectively the magnitude of gravity on that little m.
So mass is the cause, not gravity.
No, sir. You are confusing, like, just the mass, which we are not talking about.
But that's
We're talking
that's the
about
thing you're
mass getting
manipulating.
Closer.
But that's the thing you're manipulating. You're taking a mass and the distance. That is what you're manipulating. That's not gravity. Is
those are both
is a
of the
ball
three variables in the formula
is a
for
ball
gravity.
of mass gravity?
Mass is not equal to the force of gravity. No.
So, then you're not manipulating gravity. You're taking
But we
a
haven't
mass.
changed any of the masses
That's why it's
involved.
called.
You agree?
That's why it's called circular reasoning. This is
Wait,
just
hold on,
begging
hold
the
on.
question.
Before you go off on that, you agree that we have not changed any of the masses involved here, right? None of the m values are any
They're the same.
different before, during, or after the experiment.
And I would disagree and say it's not gravity that causes, it's the density.
How? Like what? The density of what?
These masses are on a torsion bar.
Yes.
They have a weight to them. The density of those weights cannot be supported by the medium around it. So it is forcing itself to seek equilibrium, which would be down. So that's what causes it to swing and have the rotational torsion
Let me just
twist.
be clear. Usually in the Cavendish experiment, you let it reach equilibrium before introducing the big masses. So it is already at equilibrium. It is motionless, or as motionless as you can possibly get it, hanging there on that wire with just the two little m's. Before you have introduced any of the big m's, it is not moving one way or the other significantly, right? So it is at equilibrium before you introduce the big m's. Now, once you introduce the big m's, how does that change anything about any of the masses or density?
How did you account for any other variables?
Well, there are variations of the Cavendish which are done in a Faraday cage or grounded to account for electrostatics.
And a vacuum.
What other things would you account for?
A vacuum?
It's done. They've done it in a vacuum before. They've done it under lots of different circumstances.
And how great can we get a vacuum with a Cavendish in it? There would still be air pressure inside that system, correct?
Very, very minimal.
And do you understand Bernoulli's principle?
Yeah.
So it would cause a lower pressure between the two masses, which can help cause the air to move through it, which pull the two.
That's not. I don't think that follows from Bernoulli's principle.
Yes, a wing, just like Bernoulli's principle, when an aeroplane flies, how the wing is situated, it flies, the lower pressure, which causes it to lift up. It's the same thing.
It's because the aerodynamics of the wing cause the air to move faster above, which decreases the pressure above, which
yes,
keeps
Bernoulli's
the wing
principle.
up
So
with
the
lift.
air, if you've got the two masses together and there's air in there, it forces itself through.
But it's in a vacuum.
So there's still air in there. You don't get
Like
perfect. You don't get a perfect
a few
vacuum.
atoms of it.
You don't get a perfect vacuum. What's the best vacuum we got on Earth?
I don't know. Good enough.
10 to the minus 6. 10 to the minus 6 Tor. That's the Sandusky, Ohio, and that is
Well, let
not
me just ask
even
you- let me just
close
ask you,
to space.
because you understand the relative here, right? So if your independent variable is the amount of air molecules, right? You're talking about whatever the best vacuum we can get is versus no vacuum at all. Your independent variable is the amount of air molecules. Are you going to see that big of a difference in the dV of this experiment?
I've seen
with manipulating that independent variable.
I've seen the Cavendish done, which the masses go opposite the direction. I've seen the Cavendish where it does absolutely bugger all. And yes, I've seen even electrostatics do cause it to move. Statics causes it to move. The fact of the matter is the masses are denser than the air around it. Now, when you're taking that medium away, it's still going to be having a greater it has less support on it, so it wants to go down more. And because it's torsioned, and if you look at the torsion wire, you would agree it's built with fibers, correct? So it has a rotation to it.
Yeah, but it's already achieved equilibrium.
No, there's no such thing as achieved equilibrium. It seeks equilibrium, but there's no such thing as equilibrium. It's static.
It's in a potential well.
A static equilibrium. Yeah, but the thing is, if you don't realize, everything you've been saying tonight is, I already believe gravity, so therefore it is gravity. I believe there's a gravitational pull, so therefore it is. I mean, you've even
in this
stated
case-
in the beginning that gravity is not a force, so you cannot take this and claim gravity to be doing anything because you're not
I want to be
manipulating
clear.
it.
In this case, right, all other plausible explanations have been debunked. Like, the only known physics, if you want to say it's some unknown physics that's causing this, sure, I guess. But again, of all the known physics, nothing else can accomplish these results other than gravity.
Gravity doesn't exist. Gravity has not even proven. Remember, you're supposed to
But
be
that's
giving.
your claim,
No.
though. I haven't heard any
You're
substantiation of that claim.
you're supposed to be giving me a scientific hypothesis and experiment for gravity. You are giving
This
me
is.
no. You are giving me something mass attracting mass, as you put it, and saying it's because of gravity. I want you to show me gravity, not mass attracting mass, because I can give an
Okay.
explanation, you can give an explanation. The
So-
problem is you're not manipulating your independent variable here.
I just showed you the independent variable that's being manipulated.
No,
I don't understand,
mass is
I don't
not
understand
gravity.
I don't understand your disagreement with my explanation of the independent variable in this experiment.
Because the independent variable is the cause for the effect observed. You are claiming gravity is the cause for the effect.
Yeah.
Okay? So
Yep.
you have to manipulate the cause. You're not manipulating the cause.
No, that's what is happening here.
No, you are manipulating the masses and their distance.
That is manipulating gravity.
Again,
Okay, look.
again, is mass gravity?
Obviously not.
So you're not manipulating gravity then. That's my
But we're not
point.
manipulating the masses. We're not changing the masses.
So
of
you
anything
don't
involved.
change the distances between the masses, how much mass?
Is that changing the masses? I'm sorry, but no, it's not. Changing the distances between masses doesn't change any of the masses involved. So it's kind of a straw man to say that I'm saying that gravity equals mass when no, the independent variable that is changing is not mass.
Okay, so
You can
distance
say,
distance
okay,
is
distance.
so distance is the independent variable.
Sure. Now here,
So not
what
gravity.
you need to do is think about the free body diagram on that little m. I'm really
I
want to get your
understand. I understand
cooperation
what
here
you're
to-
saying, but you're not getting. You are manipulating distance. You're not manipulating gravity. Distance is not gravity.
Do you agree that in the hypothesis, manipulating the distance between the masses does manipulate gravity? That is
No.
what our hypothesis is.
No. Your hypothesis is gravity causes mass to attract another mass. That's your hypothesis, correct?
Sure.
Okay. So the independent variable would be gravity, not the mass or the distance.
Well, no. Look.
Then you should say. Then your hypothesis should say distance is the cause for mass attracting mass.
Let me just clarify here, right? Our hypothesis is that there's an attractive force between masses that varies with the inverse of the distance. That is the hypothesis. So then, by that hypothesis, I would predict that if we move two masses closer to each other, their attractive force should increase. That is the hypothesis. That is the prediction. And that is what is being tested here.
So still not gravity then.
No, again, the attractive force between objects that varies inversely of their distance.
but again-
that is the hypothesis that is being tested. And we
gravity's-
are manipulating gravity. And again,
No,
that
you're
is the Newtonian regime definition of gravity.
So what is gravity then?
In Newtonian or in Einsteinian regimes? What do you want to know?
There is no such thing as Newtonian gravity. It was superseded 108 years ago.
So I just want to make sure we still use the formulas of Newtonian gravity because they work under certain conditions. If you have a relatively low gravity or a low speed, you can use those equations. So it's a little weird to say Newtonian gravity doesn't exist.
It superseded
If you wanna
108.
say-
It
but
superseded 108 years
Einsteinian
ago.
relativity will get you the same results as Newtonian mechanics, but it will do so. It's got much more broad scope. It's more comprehensive. It's more rigorous.
Okay, yeah, like you're using the tensors and so forth because you're trying to.
I'm not
Okay,
equipped to
the
have a whole
metric tensors,
conversation on tensor calculus, but yes, the Einsteinian field equations are much more accurate in much more conditions than Newtonian.
So when you're using the metric tensor, it's just simply taking, let's take a block, for for instance, in a fourth dimension, and it's tweaking it in different vectors, you could say.
You mean four-dimensional, not
dimensional.
The fourth dimension.
Fourth dimensional block. I'm just giving you a little
Yeah.
thing. But anyway, the point is, it was superseded. And if it's superseded, it means gravity is no longer a force. So therefore, you can't have mass attracting mass because you require a force for this to happen. We can't observe the fourth dimensional mathematical construct anyway.
We do, but hold on. There's a bit there I need to discuss. So first of all, just because gravity is a pseudo force in general relativity, that doesn't mean that we cannot measure it as a force. In the same way that we can still measure centripetal and centrifugal forces. You can measure those in an experiment. You can measure them in newtons, the unit of force. You can still measure those forces, just like you can measure the force of attraction between things. That doesn't mean that, just because it's a pseudo force doesn't mean it cannot be measured as a force.
Great. So a pseudo force requires a actual force for it to arise, correct? Like a turntable, for instance. There's an actual force turning that turntable to create the centripetal forces.
I don't know if that's necessarily the case, that a pseudo force always requires a force to exist. I do not know if that is a law of physics.
F equals ma. Force, it requires a mass to accelerate.
You've already said that you don't want to. You say that Newtonian mechanics is not real. You say so we cannot use F equals ma.
No, I never said that.
Newtonian.
I never said that. I said we use classical mechanics. It works every day. The problem is when you're placing that G as gravity and saying it is a gravitational force. That's the issue. Because you
but
don't.
That is Newtonian mechanics.
No, it was never actually scientifically being validated. It has never been.
But it has, though. Come
Where?
on.
You still haven't told me what is gravity. You still haven't
I did.
manipulated.
I started this conversation off by telling you what is gravity.
No, you said it's based on a not force, but because of classical mechanics, therefore it is a force. We can count it as a force.
Curvature of space-time.
Curvature of space-time is a man-made construct. Space
No,
and
it's
time are
not. It's
both
measured.
man-made. Space and time are both man-made concepts. They don't exist.
Well, we can
are
measure the curvature of
three-dimensional.
space-time.
We are three-dimensional beings. You cannot observe something in the fourth mathematical dimension.
Again, just to be very clear, we are four-dimensional beings. I don't know why you can't agree that
We're
time
not fourth
is a
dimensional.
dimension.
Time is not a thing. It's a concept. We have length, breadth, and width. That's it. We don't have
And
time.
we go through time.
No, what is time?
Time is a dimension.
No, what is time?
Okay,
Because this is what we said. This is what I said with
Let me
Matune.
explain.
What
here.
is time?
I'm trying to explain. Okay, so dimensions are how you can stipulate things. If you want to say where I am, right, you would have to give a units, right, in three-dimensional space for my location. But you'd also have to give a time for that location, right? Because I could be a different place tomorrow. And if you don't specify the time, then you haven't fully stipulated my location. That is why
reference.
that is what dimensions do functionally. So that is why we are four dimensions, because we exist at a time point.
No, time is a reference datum made by man. We
So is
literally
space.
No, space is just the absence available probability. It's just available space.
That's not what space is.
That's what space is. If I have a cube of nothing, there's availability in that cube of block. That's what space
Well,
is.
if you have a cube of nothing, then you don't have any space in there either.
It's availability.
Means no space, no time.
Space means availability. That's what space means.
No, that is not the case, because
Okay, what does
time
space
is
mean?
also availability. So by your
Time
own
is not
definition,
availability.
by your own definition, time is also a dimension, just like space.
No, space is not a dimension. We have length, breadth, and width. Just like you have that cube to say space, that availability, length, breadth, and width. That's it.
Yep.
There's no
The same with
fourth-
time, though. You have availability in time as well.
No, time is a reference, man-made reference on a timeline, so you can work out certain
But
units.
space is a man-made reference on a spatial line. You
No,
know, we
that's
invented meters
mathematics.
and feet.
Do you understand what it means when you say space availability?
Yeah, things can be available at different points in space. There's potential at different points.
Great.
The same thing applies to time.
So does that make it fourth dimensional, or does that just mean in our three-dimensional reality, if I move into that available space, I've just filled that available space?
It's the exact same thing with time, yes.
Great. So we can understand space itself is not physical.
I disagree with that.
Space is physical. So availability, there's nothing there. Something.
No, there's not nothing there. There's space there. Space is not nothing.
It's availability.
No, it is actually not, but, you know.
That is, it's availability. That's what space is.
I'm sorry, but you will find no citation for this claim of yours that space is availability. I mean, that's a you thing. That's your idea.
Why do they call it space then?
I don't know the etymology of the word space, Flatzoid.
But you just said it's not the reason, so you have to tell me what space is, because you're making a claim now that that's not what space is.
I know 100% that space is not nothing, because nothing is no space, no time, no energy, no matter.
Again, time is a man-made construct. Space is just availability in our three-dimensional reality. That's it.
How much do you understand about Lorentzian transformations in Minkowski four-dimensional Riemannian manifolds? Because that would be how you would go about understanding why space and time are the same manifold.
Those are just based on the line constructs. That's what I'm saying. It's a mathematically based.
The line constructs?
Line. Let's put it this way. If you do a calculus, you're going to have the x and a y. Okay? You're going to put the space on the one, you're going to put the time on the other.
Okay.
Okay, then you're going to do your linear function. You're going to show, okay, it's bending on the y-axis and on the x-axis, and therefore you have space-time bending. It's just mathematical.
So then let's talk about the actual physical observations of space-time bending then, shall we? Gravitational lensing, gravitational redshift, gravity waves.
You haven't proven gravity to be able to make those claims yet.
It doesn't matter though. Let's ignore gravity entirely. Let's say that gravity, we don't know anything about it. Let's just go with the observations. And what we are observing is space-time curvature of space-time. Those are the observations regardless of what we know about gravity.
But we can't do that because time is a man-made construct. It's literally just a reference given by man. Space is just availability in our three-dimensional reality. You want to stick them together and call it fourth-dimensional, which is just mathematical. We can't observe because we're three-dimensional beings. Doesn't make it observable in the fourth dimension.
We do observe gravitational lensing.
We don't.
I hate to break it to you.
You don't.
We do. You want to see pictures of it?
Again, you do not observe what you're claiming. It's just begging the question. How do you prove that is what you observed?
So here you go. With gravitational lensing, the reason why we know that it's due to the curvature of space-time is because we know how optics works. Right? You agree? We understand optics.
Very well. Yeah.
Okay. So using everything we know about optics to explain gravitational lensing only gives you half of the effect, right? You would predict a strength of the gravitational lensing to be exactly half of what it is. But using general relativity, you precisely predict what the magnitude of gravitational lensing is. And that's verified thousands of times in the sky whenever we look at and observe gravitational lensing.
Again, this is just begging the question. You're literally doing circular reasoning. You're saying it is gravity that's causing this. How do you know it's not something else?
Well, again, it could be something else. That's new physics. It would take something that we don't... It would have to be new physics to explain it, because optics and all other known physics do not explain it. But we can predict exactly what the observations are. We can predict it very, very precisely with general relativity. So if you want to say that it's not actually gravity, then you'd have to explain why general relativity works so well, or
but general relativity breaks.
That it's some kind of unknown physics.
But general relativity breaks down when you bring up a three-body, when you stick in a third body of mass.
That is actually a common misconception and not true.
Okay.
It just becomes much more complicated to solve mathematically, but it has been done.
Have you done it before?
No,
or know anybody who's done it before?
Versed enough in tensor calculus.
Or know anybody that's done it before?
Personally, no, but we can go and look at the math itself. I mean, it has been done.
Okay, so this is going to get back to my point. So if we get to a person that, let's say, makes a prophecy about something happening in the future, and that happens.
Yeah.
Okay.
I am much more liable to believe what they're saying if their prophecies are correct. Absolutely.
Okay. Does now that make it scientific?
Well, if their prophecies are going from a hypothesis to verified observation, and that's repeatable for multiple people.
I can do this with the Bible. This prophecy's been for thousands of years said in the Bible, and it's coming to fruition now. Would you say that's science? Would you say it's scientific?
Well, I disagree that those prophecies are coming true. So
no, they're definitely going. You might need to read your Bible.
That will clear things up.
Maybe you don't know how a hypothesis works, because to do a hypothesis, you have to assume a cause, correct?
Sure.
So that's not begging the question.
But again, it's not explaining anything either if you just assume that, like, if I'm asking you to explain why the downward vector, and your cause for that already inherently assumes that the vector is downward, then it's not an explanation. It's begging the question.
Okay, the observed phenomena would be the density ratio of the object relative to the medium. Sorry, let me just... Relative to the medium causes the vector. Correct?
Sure.
Okay. So, what is the IV? The IV...
Wait. That's not your
density-
observed phenomenon. That's your hypothesis.
Yeah, but I'm just saying we observed it. I'm giving the hypothesis now.
But
We
wait, we
observed
don't
it for-
observe that it causes the vector.
Observed. I'm going to put this.
So just delete the causes the vector
rock,
part.
Rock falls. There we go. Is that what you want?
Okay, yeah, and then change the observed phenomenon to hypothesis.
No, that is hypothesis. Observed phenomenon is part of
I know
hypothesis.
that is your hypothesis. Your hypothesis
Great.
is density rate.
Yes.
Okay.
Great. So the IV... And now to just release this one. So the IV would be the density ratio between the object and medium. You would agree with that?
Sure.
Okay. The dV would be the acceleration either acceleration with a vector.
Well,
of
dV
this-
is
well,
vector.
Yeah, the vector. I'm just going to say the vector because it has acceleration. The vector of the object. Now experiment. Oh, I didn't write it. Experiment. Changing the ratio between the object and the medium.
Yeah, I get it.
Causes
you can manipulate the various
the
density
vector.
ratios, and you can get it to be buoyant or you can get it to go down. I get it.
Okay, now I'm going to quickly draw it for you in very simplistic terms. This is a container with water. It's normal fresh water. And we're going to say, we're going to do an egg just because we got the egg on there. Why not? We're going to put the egg there. The egg is just floating nicely in there.
Yeah, I got you.
Okay. Now
This is very tedious.
Obviously.
Say.
Okay, but I just have to get because I know some people don't understand this. Okay, then we put it in the same container. Now we just changed the density of the water, so we made it denser now. Okay. Sorry, we've made the water. Well, this is the denser. Sorry, this would be the salt. This would be fresh water. So the egg would go down. correct? Because it's less dense.
Sure.
So
I mean, I'm not disagreeing with how density works. I just want to make that clear.
yeah, less dense, more dense. What did we see here? The ratio has changed.
Okay.
So the vector.
I agree. That,
the vector.
I mean, I agree with how density works. I'm not disagreeing with density here.
Great, but
Or
I'm saying, but I'm
buoyancy.
telling you, this is simply what we observe in reality, and based on science, we can validate that this is the reason. Now, you asking me specifically why down and why not up? This is the reason, because the ratio